Hello my friends and welcome back to the You Can Do TV channel. The Alaskan Way Viaduct demolition reveals one of the most technically demanding demolition projects ever undertaken in an urban environment. With more than 3 decades of experience, the project team described this job as uniquely challenging due to the extreme proximity of active buildings, live traffic lanes, and pedestrian areas. The viaduct, built 50 to 60 years ago, used structural systems very different from modern bridge design. The demolition process began with slotting the deck, punching out the roadway sections between girders. Hydraulic hammers were used, wrapped in rubber to suppress dust and prevent flying debris. To protect nearby buildings, full-height protective curtains were installed and maintained at all times, forming a critical barrier between the work zone and surrounding properties. Upper girders were removed, using the largest high-reach demolition machines available, capable of handling massive reinforced concrete elements. When working close to buildings, girders were carefully cut into sections and lifted out by crane rather than dropped. Columns were then systematically munched down in a controlled sequence. Lower deck sections and footings followed, requiring precise coordination between excavators, cranes, and support crews. Material handling was another major technical challenge. The volume of debris was enormous, making immediate hauling impractical. Instead, material was flattened and processed on site. Rebar was separated, cut, and bundled, with some bars weighing up to 35 pounds per foot. Concrete was crushed and recycled, contributing to a project recycling rate of nearly 99%. Recycled concrete was later reused in tunnel backfill, closing the material loop. Safety and communication were central to operations. Operators worked in extremely tight quarters, often with limited visibility due to dust, sunlight, and water spray. Two-way radios were essential, supported by spotters, water crews, and personnel in man lifts who acted as the operators' eyes. Every movement was coordinated in real time. Ultimately, the demolition not only removed aging infrastructure but reshaped Seattle's skyline. Through careful engineering, disciplined execution, and constant communication, the Alaskan Way Viaduct was dismantled safely, efficiently, and with minimal impact on the surrounding city, demonstrating demolition as a precise, high-level engineering discipline rather than simple destruction. The pouring of the 3 millionth cubic meter of concrete at the Yusufeli Dam marks a major milestone in the project's construction. When completed, Yusufeli Dam will become the world's 3rd highest double-curvature concrete arch dam, representing a remarkable achievement in dam engineering. Concrete placement on the dam body continues at an average rate of 400 cubic meters per day, requiring strict control of temperature, curing, and placement quality. Upon completion, the total volume of concrete used in the project is expected to reach 4 million cubic meters. Reaching this stage highlights the success of advanced construction techniques, precise logistics, and continuous quality monitoring. The Yusufeli Dam stands as a symbol of large-scale hydropower engineering and Turkey's growing expertise in complex infrastructure projects. The Nissibi Bridge is more than a transportation project. It is a landmark of modern Turkish engineering, perseverance, and national pride. For centuries, Adıyaman stood at the crossroads of civilizations, and in the 1990s, a new symbol was added to its history: the Ataturk Dam, one of the largest projects of the GAP development program. While the dam brought prosperity, it also flooded the old Kata-Siverek route, forcing people to cross the reservoir by ferry. Long queues, lost time, disrupted trade, and strained social ties made a permanent solution essential. In 2011, the General Directorate of Highways launched the tender for the Nissibi Bridge, designed to reconnect Adıyaman with Şanlıurfa and Diyarbakır along State Road 630. The project was awarded to Gürsan Holding, and construction began in the summer of 2012 near the Kata-Siverek ferry line. From the start, Nissibi was a project of firsts. After the Bosphorus bridges, it became Turkey's longest mid-span bridge, the longest cable-stayed bridge with an inclined cable system, and most importantly, the first major suspension-style bridge, fully designed, built, and supervised by Turkish engineers and workers. Every element, from engineering services to materials and workmanship, was delivered using domestic resources. The construction site demanded extraordinary groundwork. At the locations of the two pylons, 150,000 cubic meters of blasted excavation were carried out. Each pylon rests on a foundation covering nearly 1 decare. The pylons themselves rise 96 meters high, shaped like an inverted Y. Geological surveys confirmed extremely strong limestone bedrock, capable of carrying loads equivalent to several fully loaded trucks per square meter. To build these massive pylons, 31,000 cubic meters of high-strength concrete and 200 tons of reinforcement steel were used. Due to dense reinforcement, C50/60th self-compacting concrete was selected, capable of carrying over 600 kilograms per square centimeter. Because the bridge is located in a seismic zone, it was designed to withstand one of the most severe earthquake scenarios imaginable, with a 475-year return period, while remaining elastic and fully operational afterward. Steelwork formed the backbone of the deck. In total, 500 tons of steel were used, enough to build a full-scale Eiffel Tower. Prefabrication took place in Osmaniye, where steel elements were produced, transported by special trucks, and assembled on site into segments weighing up to 250 tons, each covering 440 square meters. Heavy lifting operations required custom-designed equipment developed by Gürsan engineers. One historic moment came when a 250-ton segment was lifted for the first time. Precision was everything. Every centimeter mattered. Welding followed, with crews working day and night. Across the entire bridge, an astonishing 712 kilometers of welding seams were completed. Cable installation marked another critical phase. Each segment is supported by 2 cables, formed from bundles of 7-wire strands. The bridge carries 80 cables, ranging from 67 to 117 meters in length. Cable installation was performed symmetrically to maintain balance, with each pair taking 2 days to complete. One of the most challenging operations involved lifting segments over the reservoir itself. Segments were placed onto barges, transported by ferry, and lifted to positions 34 meters above water, a process that could take up to 8 hours per segment. Unexpectedly low water levels during a severe drought forced engineers to improvise. extending a carrier beam by 17 meters and transforming it into a self-supporting structure, saving months of delay and millions in costs. Throughout construction, temperature variations were closely monitored. A 10-degree daily temperature change could shift parts of the structure by 10 centimeters, requiring constant recalculation. Sensors continuously tracked wind, humidity, seismic activity, and structural movement. Finally, in a moment filled with tension and pride, the last 6-meter key segment was lifted into place, as commands echoed, "Pull, follow the gauge, lift." The bridge was completed. In May 2015, the Nissibi Bridge opened to traffic, reuniting Siverek and Kata, restoring social ties and revitalizing trade. Today, the Nissibi Bridge stands as Turkey's third-largest cable-stayed road bridge, and a symbol of what national engineering, safety, environmental responsibility, and determination can achieve, without a single fatal accident, and with respect for both people and nature. The Deal Beam Shifter plays a critical role on the Indian Street Bridge, also known as the Veterans Memorial Bridge, connecting Palm City to Stuart, Florida. Used by Archer Western contractors, this specialized piece of equipment is designed to precisely lift, transport, and position massive bridge beams with exceptional control. Operating on the bridge deck, the beam shifter allows crews to move heavy precast girders laterally and longitudinally without the need for repeated crane lifts. This improves safety, reduces construction time, and increases overall efficiency on a constrained worksite. The machine's hydraulic systems provide smooth, accurate movement, ensuring beams are aligned to exact tolerances before final placement. Its use highlights modern bridge construction techniques, where advanced equipment enables faster installation, minimized traffic disruption, and improved quality control on major infrastructure projects. China's high-speed railway bridge construction process is a powerful demonstration of modern engineering, industrial organization, and construction efficiency on a massive scale. As high-speed rail networks continue to expand across the country, elevated rail routes play a critical role by freeing up ground space, reducing land occupation, and providing a smoother, more stable ride for trains traveling at extreme speeds. At the core of these elevated structures are large box girders, which form the primary load-bearing system of most high-speed railway bridges. Box girders are manufactured using pre-stressed concrete combined with structural steel, allowing them to carry enormous loads while resisting deformation. Instead of being built on-site, these components are pre-engineered and prefabricated in dedicated production facilities. The manufacturing process is highly standardized and strictly controlled, involving 9 major stages and 18 detailed procedures, from raw material preparation to final curing. Each girder requires approximately 42 days to complete and can weigh up to 1,000 tons, yet is designed to endure extreme environments, including strong winds, water infiltration, high heat, and severe cold. Once completed, the girders are transported to the construction site and erected using specialized launching gantries and heavy lifting equipment. On-site, the girders are accurately aligned and bolted together, forming a continuous, rigid bridge deck. This modular assembly method significantly reduces construction time, while ensuring consistent quality and structural integrity across hundreds of kilometers. Track installation above the bridge is equally advanced. China employs the CPG 500 ballast track laying machine, one of the most advanced systems of its kind. This machine can lay up to 2,000 meters of rail per day. During operation, 30-ton, 500-meter-long steel rails are installed in a single continuous process, with both rails laid simultaneously. The system precisely adjusts rail spacing at 60-centimeter intervals, ensuring perfect alignment. Long stretches of rail are instantly transformed into a continuous welded track, improving ride comfort and reducing long-term maintenance. This technology was clearly demonstrated during the construction of the Datong-Zhangjiakou high-speed railway, where 280 kilometers of double-track line were completed with remarkable speed and precision. The efficiency, accuracy, and visual order of the process impressed viewers worldwide, with international audiences praising China's construction capability and technological advancement. By combining prefabrication, automation, heavy machinery, and strict quality control, China's high-speed railway bridge construction achieves world-class efficiency, durability, and precision, setting a global standard for large-scale infrastructure development. The ASTRA Mobile Baustellenbrücke represents a groundbreaking solution for highway construction under heavy traffic conditions in Switzerland. With constantly increasing vehicle density on national roads, traditional roadworks create significant congestion, safety risks, and operational inefficiencies. The ASTRA Bridge concept addresses this by allowing traffic to flow above while construction continues underneath. The bridge spans 236 meters, with a central 100-meter work zone offering a free clearance of 3.10 times 5.10 meters, enabling the use of modified heavy equipment for efficient work beneath the bridge. Two narrowed lanes remain open on top, maintaining traffic flow without the usual lane closures. Assembly of the bridge is highly modular and mechanized. Ramp elements, intermediate segments, and portals are transported via tyflators and positioned with hydraulic systems capable of precise adjustments to millimeter accuracy. The two 33-meter ramp halves are aligned and bolted together using powerful short-stroke hydraulics, while intermediate segments hang on massive pins, allowing controlled movement during bridge positioning. Each 35-ton portal can be prepared and maneuvered by a single operator in about 30 minutes, with hydraulic footplates providing stability and precise alignment. The ramp slope is 6.1%, and a total of 88 GPS-guided wheeled platforms ensure synchronized movement and accurate placement of all segments. Construction requires meticulous choreography. Cranes unload heavy elements, hydraulics lift and secure segments, and all mechanical and electrical systems are synchronized to ensure seamless operation. After assembly, the bridge allows 2 lanes of traffic to flow while construction continues underneath, eliminating traditional lane shifts and reducing risks for both workers and drivers. The bridge underwent extensive testing, and initial deployment on the A1 in April 2022 demonstrated its effectiveness, with minor ramp angle adjustments planned for optimization. The project demanded over 15,000 engineering hours and tens of thousands of operational hours for fabrication, assembly, and testing. With its innovative design, mechanization, and modular construction, the ASTRA Bridge sets a new standard for fast, safe, and efficient highway construction while maintaining continuous traffic flow. The deep foundation works of the Dubai Creek Tower represent one of the most advanced foundation engineering projects ever executed. Carried out by Sultan Bachi, the work supported the future observation tower designed by Santiago Calatrava and commissioned by Amar Properties as the centerpiece of Dubai Creek Harbor. From the outset, the project combined extreme loads, complex geometry, and a highly compressed schedule. Site setup and grading began in July 2016, followed by preliminary test barrettes in August 2016. These tests set a world record in load testing, with a combined load of 300 tons applied to a single barrette using O-cell technology, validating the design assumptions. Between October 2016 and February 2017, 145 core barrettes were constructed to depths of up to 74 meters using 4 hydrophrase cutters. The operation consumed approximately 220,000 m³ of polymer-based drilling fluid and 16,000 tons of reinforcement steel. A further 328 wide barrettes, each 6.2 meters wide, were installed for the cable array system between April and July 2017. The works also included a 72.5 meter diameter diaphragm wall, 66,000 m³ of bulk excavation to 16 meters depth, and placement of 90,000 m³ of high-strength concrete. Completed on the 30th of July 2017, the project required over 1.2 million man-hours, with up to 800 personnel on site daily, showcasing world-class execution in deep foundation engineering. Stress light tanks are advanced precast concrete storage solutions engineered for durability, efficiency, and rapid installation. The Stress Light Precast Concrete Tank is a modular post-tension system designed in full compliance with BS 8007 to 1987. Ensuring structural integrity and long-term watertight performance. Post-tensioning applies controlled compressive forces to the concrete panels, significantly reducing cracking and improving resistance to internal pressures, making these tanks suitable for water, wastewater, and other liquid storage applications. All Stress Light tank components are manufactured in controlled factory conditions using high-quality concrete and intensive vibration techniques. This process produces dense, uniform panels with excellent surface finish, enhanced durability, and extended service life. Factory production also ensures consistent quality, precise tolerances, and reduced risk of defects compared to in-situ construction. The modular design allows for fast and efficient on-site assembly. Installation requires fewer personnel and less heavy equipment, resulting in lower labor costs and improved site safety. Typical Stress Light tanks can be fully installed, post-tensioned, and water-tested within 2 to 3 weeks, allowing the system to be brought into service much faster than traditional cast-in-place tanks. Stress Light tanks offer exceptional flexibility in design. Each tank can be custom engineered to accommodate specific pipework layouts, inlets, outlets, access hatches, and internal equipment to meet individual customer requirements. The system supports a wide range of capacities and configurations, making it suitable for municipal, industrial, and agricultural projects. After installation, tanks undergo a rigorous water test to verify watertightness and structural performance before commissioning. With their combination of structural reliability, rapid installation, and design adaptability, stress-light tanks provide a cost-effective, long-lasting solution for modern liquid storage infrastructure. The construction of the Ahrensfeld-Wittefeld Wind Park in Bromsha is a complex, precisely coordinated process that combines civil engineering, heavy lifting technology, and renewable energy expertise. The project begins long before any visible structure rises above the ground. First, the soil is carefully prepared. Earthworks stabilize and level the terrain, ensuring it can safely support the extreme loads generated by a modern wind turbine. During this phase, empty conduits are installed underground to later accommodate power cables, control lines, and communication systems, protecting them from environmental damage and mechanical stress. Once the ground preparation is complete, work begins on the foundation. An outer formwork is assembled, defining the massive circular base of the turbine. Inside this formwork, a dense reinforcement structure is built. Around 85 tons of reinforcing steel are installed, forming a complex cage that provides the foundation with the strength required to withstand wind forces, rotor torque, and continuous dynamic loads. Concrete is then poured in a single, carefully controlled operation. After casting, the foundation is left to cure and harden, reaching full structural strength over time. When curing is complete, internal stair elements are installed, and the electrical trench connecting the turbine to the grid infrastructure is laid. The next major phase is tower construction. Tower segments are delivered to the site in a tightly scheduled sequence. To assemble the main lifting equipment, 2 auxiliary cranes are first required. The concrete tower is erected using a 500-ton crane, capable of lifting heavy components to heights of up to 90 meters. The tower itself is built from prefabricated concrete half-shell segments. These segments are assembled ring by ring, stacked precisely on top of one another. A climbing working platform moves upward with the structure, allowing crews to work safely and efficiently at height. In total, 9 additional complete concrete rings are installed, and the concrete tower construction phase takes approximately 15 days. Once the concrete section of the tower is complete, stabilization cables are drawn into the structure. These internal tensioning systems enhance long-term stability and help control vibration. Aerial inspections provide a clear overview of alignment and geometry. Above the concrete tower, 2 steel tubular sections, each weighing around 50 tons, are installed to complete the upper portion of the tower and prepare it for the nacelle. The installation of the nacelle marks one of the most demanding stages of the project. This operation requires a 750-ton heavy-lift crane with a hook height of up to 145 meters, supported by an additional crane for guidance. The nacelle houses the turbine's core systems, including the generator, gearbox, and control electronics. Lifted in a single, slow, and precisely controlled movement, the nacelle is positioned onto the tower with millimeter accuracy. Inside, the drivetrain is aligned and secured, forming the mechanical link between rotor and generator. The final and most spectacular phase is rotor installation. Each rotor blade measures 59.8 meters in length, making them extremely sensitive to wind conditions during lifting. One blade at a time is hoisted and attached to the hub. The first blade is mounted, followed by the second, and finally the third. During these lifts, operations pause frequently to monitor wind speed and direction. Spectators and crew alike hold their breath as each blade slowly swings into position and locks into place. With all three blades installed, the turbine reaches its full form. What began as prepared earth now stands as a fully assembled wind energy system. From foundation construction to tower assembly and final rotor installation, the wind park at Ahrensfeld-Wittefeld demonstrates how precision engineering, heavy machinery, and careful planning come together to deliver sustainable energy infrastructure for the future. The border stretches for miles, remote, exposed, and difficult to secure. Building a permanent structure here is not just a construction challenge, but a logistical one. This is where the Wind One Pass trenching technology changes the game. Designed for extreme precision, the De Wind trencher operates just 2 inches from the border, cutting a foundation 6 feet wide and 8 feet deep in one continuous pass. There is no stopping, no repositioning. As the machine advances, it excavates and simultaneously mixes native soil, dry Portland cement, and water, creating a stabilized soil cement foundation in real time. Truck after truck delivers dry cement, which is blown into the trencher's metered auger system. From there, material is precisely dispensed into the trench, where the high-speed digging chain homogenizes the mix. Alignment is critical. Marker stakes guide the operator, ensuring the foundation follows the borderline with absolute accuracy. Security is maintained throughout the process. Temporary wall panels are removed and replaced daily, ensuring the border remains protected at all times. Once the foundation has cured, the top 12 inches are removed to create a level surface. A centered key trench is then cut to receive the permanent wall panels, later locked in place with concrete. Dewey's one-pass system delivers unmatched production speed, fewer machines on site, and exceptional accuracy under tight constraints. It's not just trenching, it's precision engineering in motion, turning difficult terrain into a stable foundation for long-term infrastructure. The Narendra Modi Stadium, formerly known as the Motera Stadium, stands as one of the most remarkable achievements in modern sports infrastructure. Located within the vast Sardar Vallabhbhai Patel Sports Enclave in Ahmedabad, Gujarat, this iconic venue has redefined the scale and ambition of cricket stadium design. As of 2021, with an extraordinary seating capacity of 132,000 spectators, it is officially the largest cricket stadium in the world, symbolizing India's growing strength in delivering mega infrastructure projects of global significance. Beyond the visible architecture, the construction process of the Narendra Modi Stadium was an enormous technical and logistical undertaking that unfolded in carefully planned stages over several years. After demolition of the old Motera Stadium, engineers carried out extensive geotechnical investigations to understand soil behavior and load-bearing capacity. This data guided the design of deep foundations capable of supporting the massive superstructure, seismic loads, and crowd-induced vibrations. Thousands of piles and large raft foundations were executed with strict quality control, as even minor deviations could affect long-term performance. The structural framework was developed using a combination of cast-in situ and precast concrete elements. Large precast components, such as raker beams, seating slabs, and stair units, were manufactured off-site and transported for rapid installation, significantly reducing construction time while maintaining precision. High-capacity cranes operated continuously to assemble the circular bowl, with teams working in parallel zones to maintain progress across the vast footprint. A critical phase involved the roof and facade construction. Steel members were fabricated with tight tolerances and erected sequentially to form the continuous ring structure. Wind and seismic considerations were central, given the stadium's scale and open geometry. Advanced monitoring systems were used during erection to control deflection and alignment in real time. Simultaneously, MEP systems, mechanical, electrical, plumbing, fire protection, and IT were integrated throughout the structure. This included power distribution for lighting and broadcasting, drainage for the pitch and concourses, HVAC for enclosed spaces, and complex data networks to support security, ticketing, and live media transmission. Interior works followed, with finishes, seating, hospitality areas, player facilities, and media spaces completed in carefully sequenced packages. Finally, extensive testing and commissioning ensured that lighting, sound, safety systems, and crowd circulation performed flawlessly. This layered, highly coordinated construction process transformed an empty site into a world-class stadium, reflecting not only scale but exceptional engineering discipline and execution. The project began with the careful dismantling of the old Motera Stadium, followed by extensive ground preparation. The site was re-engineered to support a massive circular structure, requiring deep foundations and high-strength reinforced concrete. Structural planning focused on creating a column-free seating bowl, ensuring unobstructed views of the field from every seat. Advanced modeling and prefabrication techniques played a key role in achieving both speed and accuracy during construction. One of the defining features of the stadium is its continuous bowl design, which enhances crowd energy and sightlines. Over 132,000 seats were installed using a modular approach, allowing for consistent quality and efficient assembly. Wide concourses, multiple access points, and well-planned circulation routes were integrated to ensure smooth crowd movement, safety, and comfort, even at full capacity. Beyond the stands, the stadium offers world-class player facilities. These include spacious players, dressing rooms designed to international standards, complete with recovery areas and private zones. A fully equipped players' gym allows athletes to train and warm up within the stadium, while modern players' washrooms and support spaces ensure comfort and functionality. The walk-through field access provides players with a dramatic and seamless transition from the dressing rooms onto the pitch, enhancing the matchday experience. The stadium also features premium hospitality and administrative spaces. Luxury suite rooms and an exclusive presidential suite offer top-tier comfort and privacy for distinguished guests. These areas provide panoramic views of the field, blending sporting excitement with high-end hospitality. A large, well-appointed banquet hall supports official events, ceremonies, and corporate functions, making the stadium a year-round destination rather than a match-only venue. Media and broadcasting infrastructure received equal attention. The press conference room is designed to host international media interactions with advanced audio-visual systems. Dedicated media rooms, a amenity more than the opening of a sports venue. It represented India's capability to conceptualize and realize world-class infrastructure that meets international standards in design, safety, technology, and spectator experience. Today, the stadium stands not only as the world's largest cricket stadium, but also as a symbol of ambition, innovation, and national pride, an architectural marvel whose making is as inspiring as the matches it hosts. The Monaco land extension project at ASTRA Bridge marks a major milestone in Monaco's urban development. Completed in 2019, this ambitious land reclamation effort created new territory along the coastline to support housing, infrastructure, and public spaces. Advanced marine engineering techniques were used to protect the marine environment while forming a stable foundation for future construction. Massive concrete caissons were precisely placed to create a protective offshore barrier, allowing land to be reclaimed safely behind it. The project combined sustainability, innovation, and precision engineering, transforming the seafront while preserving Monaco's coastal identity. The ASTRA Bridge extension stands as a showcase of world-class coastal engineering and strategic land expansion. The removal of the Lago Terra Dam on the Bernesga River is a clear example of how modern engineering and environmental restoration can work together to repair long-standing damage to natural river systems. Built in 1922, the dam originally served a small hydroelectric facility, typical of early micro-hydro installations. Over time, the structure became obsolete, while the river section where it stood was later designated a protected area within the World Network of Biosphere Reserves, recognized for its ecological and landscape value. The dam formed a solid wall that completely blocked fish migration and disrupted natural sediment transport. Disused gates and a bypass channel showed clear signs of deterioration, and the reservoir behind the wall had become partially filled with sediments accumulated over decades. In September 2011, after the operating concession expired, the Duero Hydrographic Confederation initiated the demolition of the dam, in accordance with Spanish legislation that requires the removal of unused hydraulic infrastructure from public river domains. This intervention was part of Spain's National River Restoration Strategy, promoted by the Ministry for the Environment. The primary objective was not simply demolition, but the recovery of ecological and hydraulic continuity. Anglers, conservationists, environmental groups, and the general public strongly supported the project, recognizing that obsolete dams often do more harm than good once their original function is lost. One of the first technical challenges was site access. A significant elevation difference existed between the old road and the riverbank, making it impossible for machinery to reach the dam directly. A temporary access ramp was constructed using sediments from an old river pool and recycled concrete debris from other restoration works. Existing riverside vegetation was preserved to stabilize the ramp and minimize environmental disturbance. Before demolition began, all mechanical elements of the gates were carefully dismantled. At the same time, fisheries specialists from the Castilla y León regional government carried out extensive electrofishing operations to rescue and relocate aquatic fauna. Multiple passes were required due to the high density of fish, highlighting the ecological importance of the site. Demolition proceeded in controlled stages. An initial opening in the bypass channel allowed the water level to be lowered gradually by less than 1 meter. This careful drawdown minimized downstream impacts and preserved water quality. As expected, fine sediments were limited, and coarser materials such as gravel and stone quickly became dominant. Once conditions stabilized, heavier demolition work began. Concrete debris was temporarily reused to reinforce access routes for machinery. The most reinforced sections, particularly the gate structures, were dismantled slowly to separate metal from concrete for proper disposal. A deeper opening was then cut into the dam wall, allowing the water level to drop further and exposing sediments deposited over nearly 90 years. As demolition advanced, the river's natural processes became increasingly active. Flow velocity increased, sediments were mobilized and transported downstream, and previously sediment-starved sections began to recover. Fish remaining in the area naturally migrated upstream as barriers disappeared. Rather than reshaping the river artificially, the project focused on removing the obstacle and allowing the river to restore itself. Despite some public controversy over demolishing infrastructure, the results were clear. The project restored 16 kilometers of uninterrupted river continuity, benefiting fish migration, sediment dynamics, macroinvertebrates, and overall river morphology. It became the 75th barrier removal in the Duero Basin, part of a long-term strategy addressing thousands of obsolete structures. Within weeks, supported by modest natural flow increases, the Bernesga River largely reclaimed its original course. The La Gotera Dam removal stands as a strong example of how thoughtful engineering, legal responsibility, and respect for natural processes can successfully bring a river back to life. Bored pilehead demolition is a common construction process in foundation works. This operation is carried out to remove low-quality or contaminated concrete at the top of the pile, which often does not meet design strength requirements. The method typically uses a hydraulic breaker, suspended or fixed above the pilehead, to control impact force and direction. This approach allows precise removal of concrete to the required elevation without damaging the main pile body or reinforcing steel. Proper pilehead braking ensures a strong structural connection between the pile and pile cap, contributing to overall foundation integrity, safety, and long-term durability.
The installation of sealed wells by ZPB Kaczmarek is a highly specialized process designed to ensure durability, watertight integrity, and long-term functionality. The procedure begins with careful preparation and assessment of the subgrade. Proper site leveling and compaction are critical to provide a stable foundation for the well. Any irregularities in the soil or ground surface are corrected, ensuring the base can support the weight and pressure of the well structure. Precision in this step prevents future settlement, deformation, or leakage. Once the subgrade has been properly prepared, the installation of pipes and components begins. Pipes are carefully aligned and connected according to technical specifications to ensure seamless flow and watertight joints. ZPB Kaczmarek utilizes specialized fittings and connection systems to maintain structural integrity and prevent infiltration. Each connection is checked for alignment, proper insertion, and sealing, minimizing the risk of leaks or mechanical failures. The assembly of the well body, including elements such as HANA-ZOS SN modules, follows strict procedural steps. These components are stacked and secured using manufacturer-recommended techniques, with attention to maintaining verticality and overall stability. Each segment is carefully lowered and positioned, ensuring accurate placement and proper interface with the connected piping system. Finally, additional elements and finishing components are applied. This includes sealing elements, access covers, and any protective layers required for operational reliability. Each installation step is verified through visual inspections and, when necessary, testing to confirm the well's watertight properties and structural soundness. The process emphasizes precision, adherence to technical standards, and the use of high-quality materials to achieve a fully operational and long-lasting sealed well. Through this methodical approach, ZPB Kaczmarek ensures that each installed sealed well meets rigorous engineering requirements. The integration of precise subgrade preparation, meticulous pipe connection, and careful assembly of modular elements results in a reliable, maintenance-efficient system capable of supporting diverse municipal, industrial, and environmental applications. Meet the machine that pours concrete as smooth as cream. This high-performance tool lays flawless surfaces with incredible speed and precision. No more back-breaking labor, just perfect, even concrete every time. Powerful, efficient, and game-changing. This concrete pouring machine truly is a construction superstar.